Hello, this talk explores the use of drone swarms for real-time atmospheric characterization in the context of optical propagation. We focus on why such a swarm is useful and how we developed a working prototype. To give some context, light doesn't always travel in a perfectly straight line through the atmosphere. It is influenced and redirected by it. This leads to several undesired effects such as image blurring, reduced contrast resolution, and laser beam broadening, making it difficult to focus light in a tight spot over long distances. Additionally, more familiar phenomena like mirages and apparent target displacements also occur because light paths are bent rather than straight. These effects stem from underlying physical mechanisms. Among the linear effects, absorption plays a key role, including molecular absorption and absorption by aerosols, such as airborne particles. Scattering is another factor, with Rayleigh scattering and Mie scattering contributing depending on the particle size. And refraction is responsible for phenomena like mirages. On top of these, turbulence-induced scintillation arises from small variations in the refractive index of the air. This causes, for example, effects like the star twinkling and image distortion. Beyond the linear effects, non-linear effects can also play a major role. The most important one of these is thermal blooming, particularly relevant in the context of high-energy lasers, which is the focus of this research. On the right, you can see images from a simulation in which case there is no wind. So in such conditions, part of the light from the high energy laser beam is absorbed by the air, heating it up. And since hot air has a slightly different refractive index than cold air, the beam bends outward, resulting in a characteristic donut shape. And this is footage of an actual experiment with a high energy laser. So you can see in this case there is wind and then you get a sort of crescent shape. You can see how it fluctuates due to various turbulences and variations in the atmosphere. So why use a drone swarm to measure the atmosphere? In real-world high-energy laser tests, the setup often involves a ground-based laser system, sometimes mounted on a trailer with a large power supply and a target such as a heavy calorimeter, which is also placed on the ground. This means that a laser beam usually travels horizontally or often over a valley. And the atmospheric conditions are typically measured using one or two weather stations placed either at the laser or at the target. And the data from these stations are then assumed to represent the entire beam, the entire path of the laser beam. However, realistic use cases are rarely purely horizontal. For example, when targeting airborne objects such as drones, the laser traverses through various atmospheric layers with different properties. You can't realistically build many towers along this path to take measurements at every point. So the more practical solution is to mount sensors on drones. A swarm of drones allows you to perform simultaneous measurements over several paths covering vertical, horizontal and even more complex paths. Because the drones are mobile, they can also access hard-to-reach areas such as above forests, bodies of water, or off-limit terrains, where atmospheric behaviors can differ significantly. Additionally, since the swarm samples multiple points at the same time, it can capture fast-changing conditions and provide a real-time insight into what is happening along the beam, which can then be correlated to the various observed optical fluctuations and effects at the target. Here you see a picture of one of the drones used in the experiment. It's a Hexoon Edu 458, a medium-sized platform equipped with a Cube Orange flight controller. Underneath the drone you can see additional electronics carrying various environmental sensors, and on a stick mounted on the frame there are two white enclosures. These are the Stevenson shields designed to host thermocouples. They protect the temperature sensors from direct sunlight and ensure accurate readings by allowing air to flow freely around them while blocking solar radiation. The sensors mounted on the drone need to meet several important requirements. They must be lightweight, since they are carried by a flying platform, low power because everything runs on a battery, and low cost since swarm setup requires multiple identical units. As for the atmospheric parameters we measure, turbulence is captured using two thermocouples configured as a differential temperature probe. Pressure, humidity and temperature are measured using a small commercial sensor module, namely the Adafruit BME 280. Aerosol concentration is measured with a commercial indoor air quality sensor from Amphenol, which can even provide a distribution of particle sizes. Finally, wind speed and direction are estimated by the drone itself, based on how much it tilts in response to the wind during flight. Here you see a schematic showing how all the components are connected. The sensors are connected to an ESP32 microcontroller, which collects the data and performs some basic pre-processing. This processed data is then sent to the CubeOrange flight controller, which transmits everything to the ground station using the existing Mavlink telemetry. This means that no additional hardware is needed to send the sensor data. The differential temperature probe is used to measure atmospheric turbulence. It consists of two thermocouples spaced 1 meter apart, which record temperature fluctuations at a high sampling rate of about 1 kHz and with a precision of about 0.01 degrees. In the literature, turbulence is typically quantified using the refractive index structure constant. This value can be derived from the temperature structure constant, which is calculated as the average of the squared temperature differences between the two thermocouples at each measurement point. The differential temperature probe is designed to measure temperature fluctuations in the atmosphere, but ideally not those caused by the drone's own downwash. Since the drone propeller generates a significant airflow, it's important to ensure that this doesn't interfere with the measurements. According to the literature, the downwash effects drop off rapidly just outside the propeller zone. To verify this, we mounted the drone onto a wooden plank in the lab and spun up the propellers and measured the wind speed at various distances using a hot wire anemometer. The results confirmed that the wind speed decreased quickly as you move radially outward from the drone. At around 20 cm from the propellers, the measured wind speed was already below the ambient indoor air currents. And the indoor air currents were also caused by the drone itself because this was a test indoors. The air was limited to the room itself. But in any case, this suggests that it's indeed feasible to mount thermocouples onto a 1 meter stick and obtain meaningful atmospheric data largely unaffected by the drone's own airflow. During early testing, we noticed that sunlight had a significant impact on the temperature readings, and actually even regular light. Since we are measuring temperature differences, even small variations in how the thermocouples absorb light, for example due to surface oxidation, this introduced a noticeable drift when the sun was shining. To solve this, we developed a custom Stevenson shield based on the Jan Barani design guide, and the goal was to create a shield that was both as compact and well ventilated as possible while still being lightweight and mountable on the drone. These are the two large white enclosures you can see mounted on the stick in the drone setup. We encountered several other challenges during testing. First, the thermocouples produced quite a bit of noise, either from the probes themselves or from the wiring and the amplification. However, as long as this noise is statistically stationary, it can be accounted for during the data processing. So when calculating the temperature structure constant, which maps the fine scale temperature variations, the noise can be separated out, allowing us to retrieve a clean signal. Another issue was the slow drift in the measured temperature difference over time. This was traced back to the thermocouple amplifier. The amplifier included a built-in thermometer to measure the temperature as at the cold junction, but since all electronics were enclosed in a box that heats up during operation, it's an electronics box, some temperature gradient developed. The thermometer inside the chip no longer accurately reflected the actual junction temperature. As the electronics warmed up, this mismatch started to introduce a small drift in the output. To correct for this, we implemented a digital filter that subtracts the rolling average of the temperature difference, and effectively this compensates for the slow thermal drift. We also physically relocated the amplifier further away from the ESP32 because we found that that was a major source of heat. Wind was measured using the drone itself. So when hovering in place, the drone needs to tilt to counteract the wind forces, and the amount and direction of this tilt can be used to estimate the wind speed and direction. To calibrate this method, we flew the drone next to a weather station for a period of time and recorded both the actual wind speed and the drone's tilt angles. And then by analyzing this data, one can find a clear linear relationship between the tangent of the tilt angle and the square of the wind speed, at least for the range of wind speeds that we measured that day. So this provides a practical way to estimate wind conditions without needing an onboard anemometer. The calibration was done outside because the drone is actually too big for the wind tunnel we have here at the campus. The other atmospheric properties were measured with commercial sensors and will not be discussed here. Now, regarding the drone swarm itself, several constraints shaped how the experiments were carried out. One major limitation comes from European aviation regulations, which require that at least one pilot per drone is on standby, even if the drones are operated remotely, as was the case here. Coordinating enough qualified pilots on the few dry days in 2024 was already quite a challenge, and we only used 4 drones for this test. Another legal constraint is the maximum flight altitude of 120 meters, which is still pretty close to the ground. And then we limited each scenario to about 90 seconds each, primarily because of battery limitations. So for lower elevation angles of the drone swarms, the drones needed to fly up to 800 meters away, which used up a significant portion of the flight time just in transit. The control of the swarm was managed through a Python script running on a laptop, which is connected via a local network to 4 Hearlink ground controllers. Each of these communicated which one of the 4 drones, and a 5th measuring point was on the ground, was done by the weather station. So you can see a schematic on the bottom left, and on the right, you can see that the drones flew at fixed altitudes of 30, 60, 90 and 120 meters, while the horizontal distance was varied between runs to create different slant paths. You can see in the center of the picture, this was one of the few days that we could do. We literally had to fly in between rain clouds. Here are some examples of wind measurements taken during the 90-second experiments. The green line at the bottom represents data from the weather station on the ground, so it's relatively smooth and stable. The lines above show wind estimates from the drones at different altitudes, and these show more variation, partially due to the stability issues caused by the large differential temperature probe, which caught a lot of wind. Especially on this particularly windy day, wind speeds range from around 6 up to about 8 meters per second. Despite the noise, a clear trend is visible, so wind speed increases with altitude as expected. Temperature, humidity and pressure were measured using the BME 280 sensor. In this graph you can see significant fluctuations on the data from the drone 1, especially at an altitude of 30 meters. So these fluctuations are clearly unrealistic when compared to the more stable readings from the other drones. On the next slide you will see a similar pattern in the humidity data. So we suspect the issue was caused by damage to the BME 280 or the electronics connected to it. The sensor was mounted on the outside of the electronics enclosure to ensure that it measured the ambient air rather than the warmer air trapped inside the box. However, this then exposes it to the environmental conditions like the rain or actually the grass when the drone was standing on the ground. And the BME 280 is apparently known to be somewhat sensitive to environmental stress, and this could have caused these erratic readings. And this is the slide with the humidity. You can see that again drone 1 has is an outlier when it comes to the readings. Now, regarding the aerosol sensor, the values measured during flight were significantly higher than anything we had previously recorded indoors in the lab. One possible explanation is hygroscopic growth, where airborne particles absorb moisture and increase in size. So this typically occurs at the relative humidity levels between 80 and 90%, which aligns with the humidity levels we measured during the flight. Another contributing factor could be sensor limitations. The Amphenol aerosol sensor has a maximum rated operating humidity of 95%, and if actual humidity exceeded that or was close to it, the measurements may have been skewed. It's also worth noting that our humidity readings might have been slightly underestimated, as the sensor was mounted on the electronics box, which tends to be a bit warmer than the surrounding air. So finally, we were flying in between rain clouds and light rain bursts, so it's possible that the sensor picked up fine rain droplets, further increasing the particle count. And finally, regarding the turbulence, the measured values for the refractive index structure constant were extremely high. So while not impossible according to the literature, they are at the upper edge of what is typically reported. One possible explanation is the short sampling time. We used 10-second intervals to try and capture temporal variations in turbulence. However, this may have been overly optimistic. In most literature, these measurements are averaged over time spans of 1 to several minutes to reduce, to get a more constant value. And in addition to the high values, we also observed sudden large fluctuations that were never seen in lab tests. This could have been caused by several factors. One possibility is electromagnetic interference from the drone motors, although we have tested that in the more controlled conditions. Another likely cause is environmental. We were flying in between rain clouds, and small raindrops striking thermocouples could, in theory, briefly produce sharp temperature difference, corrupting the turbulence signal. So, this project was primarily a prototype to explore the feasibility of using drones as sensor platforms. One of the key takeaways was that it's entirely possible to stream sensor data over MAVLink telemetry without needing additional transmission hardware. So this means that you can essentially connect an Arduino or whatever microcontroller directly to the system and use it in many different types of experiments. We also learned that the sensor placement is critical. So drones draw high electrical power, they have motors, batteries, and generate a lot of heat. Yet many of the parameters that we measured, like temperature, humidity, and pressure, are highly sensitive to this heat. So placing sensors on or near warm electronics led to skewed data, and this was a clear lesson in avoiding naive placement. And then regarding the differential temperature probe, we found it's a convenient method, but perhaps not ideal for drones. The Stevenson shields we added caused significant aerodynamic drag and made stable flight in windy conditions difficult. More advanced solutions exist, for example hot wire anemometers for instance, and the gold standard for turbulence measurement in research remains the ultrasonic anemometer, but these are expensive and not that easy to implement as a do-it-yourself setup. Finally, so we identified a major gap in our ability to validate turbulence measurements. While we can record and calculate turbulence-related metrics, we currently lack a reference instrument like a scintillometer to compare our measurements against. And this then concludes this talk.